All right, this week we will talk about model selection with resampling, which is basically model comparison to select a better model to use. Well, resampling, we actually not talked about the resampling, but we have encountered maybe one homework question where it let you split your data into testing and training data set, if you remember. Well, this is an important concept to evaluate your model on testing data set instead of training data set. So it's one thing for a model to be able to predict well on the data it knows the answer to, which is the training data actually. And it's another thing to be able to do well on new data. Well, on this new data will usually call it testing data. And the resampling methods are a useful tool to help us with this issue. And we will discuss one of the most common ones, cross-validation, and we actually have the formal training and validation data set splitting as well. Okay, let's talk a little bit about model accuracy and assessment for a moment before we get into cross-validation and training testing split. Okay, for the model accuracy, that is measuring how close the predicted response is to the observed data. So basically how close your prediction is to the true data. Commonly, we will use this mean squared error defined as this. So it's the mean because we divided by n, and the squared error. So this is summation of the squared error or the squared residual, which is RSS divided by n. That's our mean square error. But this mean square error is computed use the data we actually used to train the model. That's the training data. And this data is that the model knows its answer. And we mentioned we care more about how well our model performs on previously unseen data, which is the testing data. A simple example would be we would not care that much on how well your model predicts last week's stock prices, because we already know that normally we want to predict something that we didn't know, right? We will need this concept of training and testing data set, this concept for model selection. So here I have an example where I use simulated data, where the data, these circles, are simulated from this true model for this with this black curve. So this is the true underlying model with this black curve. And the fit to the data we're using a linear regression, like this yellow straight line. And we also use the two different smoothing spline method, which is this light blue curve and this green curve, very wiggly curve. The plot on the right, it's showing you we are comparing this three set of methods that we fit to the model, which is this straight line, this light blue curve, and this wiggly green line. So we actually split the data into training and testing, and we want to compare their mean squared error. So this gray curve here is for the training mean squared error, and for these three methods. And this red curve is the testing mean squared error. And we want the error to be as small as possible, right? And we want to focus on a testing data set to measure the error of its prediction. So this is telling you this light blue curve is the best because it gives us the lowest prediction error on the testing data set. And actually we can also tell from this curve if we use the training data set, like the more wiggly, like this green line, it follows the data. It basically tracks your data. It will go down and down. I mean, this mean squared error, the prediction error will be lower and lower the more you follow your data. But that would actually give us a problem called overfitting. We will talk about that in a second. And yeah, I actually covered most of the material saying here, like this. Yeah, I'm about to talk about the oh, sorry. Yeah, this is a different data set simulated from this black curve. If you focus on this data, they are different, right? Because it's different model, different underlying true model. So again, this black line is the true model, and we simulate data from that black line, black curve, and fit the data with this yellow straight line and also two smoothing splines. The splines is just a smoothing method which give you different degree of freedom that controls, that controls how flexible your model is, like how close it will track your data. This is the same concept, like use testing data set and training data set for measuring the mean squared error. We should focus on this red curve, which is for the testing mean squared error. Yeah, for this two example, this example and this one, is clearly that this green model is way too close tracking the data. And you can notice the training mean square error, it goes, it's really low, but its testing mean square error is actually very high. So if you only focus on the training data, it's not giving you the truth that telling you, well, you might make the decision that this wiggly green curve is the best. You should never use this training data set to evaluate model, because this one is overfitted to your data. So yeah, we will talk about this overfit in a second. Okay, yeah, this is the formal slides for overfitting. So overfitting model, they often performs poorly on new data, on the testing data, as we already tell. On the testing data set, the error is really high. Well, the training data, it shows really low error. And if you consider, well, the black line, we already said the black line is the true relationship for those data. And the blue and gold model, this light blue and this gold or yellowish model, they're going to be better for new data that's along this yellow line. Along this black line, right? Like they're really close to this black line. And this gray model, it fit this data set, this particular data set well. But when you simulate new data from this black line, it may not track the line so much better, so much good, like in this particular data set. So basically, this green line, this gray model is way too flexible, that you follow the data too close. When we get a new data set, it may not do well. So yeah, like how can you tell if there is overfitting or not? Basically, if you like compare the mean square error measured on testing data and training data. If for the training data, the error is really low, but for the testing data is really high, the error is really high, that means this model is really overfitting. Okay, comparing the mean square error for training data and testing data. And also directly you can tell if a model is way too flexible, like it follows the data too closely, it's normally an indicator of overfitting as well. Okay, well, overfitting is a very important concept. And I remember like in industry, that's a very common interview question talking about overfitting and how will you do to overcome this problem. That would be a follow-up question. But we already mentioned we would use testing data sets, and sometimes it's called validation sets, to get a better idea of how your model perform. So these models were being tested on new data. So the models that we just showed in the two examples in previous slides. What if we do not have new data? Like we only have one data set, right, for building the model. And we do not have any further new data set for testing. Or in this case, we will pretend we do by holding out some data from the original data set. So this is validation set, is the data held out from the original model, training or fit. The model is applied to the set to see how well it does. And we train the model on training data, and we test the model on the validation set. So that's why sometimes this validation set is also called testing set. And it can be used in many ways, like the splitting of training and testing data sets. And here is a simple figure showing like intuitively what we do with our data set. So this thing is the whole data set we have, like of size n. So 1, 2, 3 up to observation n. This is our data of size n. And we can split them to half and half to testing under this like light blue rectangle. And this, the other part is for the testing. It's about like half and half split, but it's like a random draw from this original data set. See, this is our indices for the observations from 1 to n. And when we split them, see this training set have 7, 22, 13. Those are the indices for your data record in your data set. So randomly sample half of your data set as your training data set and random sample, well, the rest would be the testing data set or validation data set. Okay, well, this is another example. Well, if you still remember, we talked about the auto data set many times, and we actually discovered, well, oh, where's my, okay, there it is. So this MPG and the house power, they have a non-linear relationship. And we want to, so for this example, we want to tell how many degree of the polynomial we should use to fit the relationship between this MPG and house power. So previously we only built linear regression model where this degree of polynomial would be 1. So when we have a quadratic term in the model, the degree of the polynomial would be 2, so power 2. And if we have a cubic term, it will be 3, etc. So this is what we are measuring. We are comparing different models with different levels of different degrees of polynomial, and we want to tell which one fit the data the best by comparing its mean squared error. So on this plot is telling you for each degree of polynomial fit, this is for a single split. So for example, we split the data into like testing and training. So this is for one single split. Okay, and we also compare, like on this right-hand side, you can tell there are so many lines. So each line is for one split. So as I said, we randomly sample data from your data set to split the training and the validation. So this would be you do the sampling this many times, so many times, and you plot the corresponding mean squared error for different level of degree of polynomials, so that to make the comparison of. So yeah, on the right are the testing mean square error for each degree of polynomial fit for many different repetitions of the sleep of the sleep. Sorry, of the split between of the split of testing and training methods, testing and training data sets. Oh, wow. So, well, this validation says this method is straightforward conceptually and very easy to implement, but there are some drawbacks for it. You can actually tell from the previous, from this plot, this validation error is highly variable. So yeah, just by looking at how different those curves we had on the previous slides. And it depends a lot on which points are chosen for which sets, because every time we random sample a group of data points for training, and it could be very different for each different split. And only because only a portion of the data is used to train the model, statistical method works better, the more data they have. So because we only use the portion of the data we have to train the model, our validation set error rate is actually be overestimating what would be possible if we use the whole data set. Is that clear? Like the more data you have for training, the better your model would be. But because we only use a part of your whole data set, then the testing error is actually lower then what will you get if you use the whole data set for training? Okay, so yeah, this is the drawbacks for using a splitting of training and validation data set. Okay, well, more formally, we would use cross-validation for model comparison. Yeah, this is the way we address the drawbacks we just talked about validation sets. And cross-validation is that we check lots of different subsets, split, and average the resulting error and fit the model. That way we fit up the model. Well, sorry. Oh yeah. That way we, oh no, that's not the logic, sorry. So to address the drawbacks, we would check lots of different subset split, and average the resulting error, which is actually what cross-validation is doing. And we can also fit the model a large subset of the data to overcome like the second bullet of the drawback we just mentioned. So we have this leave one out cross-validation, and we use this LOOCV, which is short for this leave one out cross-validation. So, well, you can probably tell from the name, we only leave one out for testing. So that way we fit the model on the largest data set we could have for training, right? If we are going to split the training and the validation, like the training data set only have one data point, and the did I say it correct? Like the testing data set, validation data set only have one data point, and the training data would have n-1 data point. So I have it formally here written up, like split the data into two parts, one with this single data point, x1, and the other data set would have all the rest. We train the model on the n-1 data points, and then use the model to predict on that excluded observation, x1, and we find the mean square error for that, and we call it MSE1. And we repeat this, like this first two steps for each point in the data set. Then we average them all together. So, well, I think I have well, yeah, this is your final cross-validation error, which is the average of each, like the average of all the mean square error you got for each split. I have this like visualized LOOCV. So this is your whole data set and observations, and each time you take one out for testing and use the rest n-1 data point to run your model, to train your model, and get the mean square error for your prediction on this first observation that you just picked out for testing, right? So for this splitting, you get one mean square error, and you do it again with the second observation as your testing data set, actually your testing data point. And you use the rest, like 1, 3, 4, up to n, like this n-1 data points to train your model. And then you get another mean square error. Like when you use your prediction, comparing to this true observation for the second data point. So you get your mean square error 2. And as so on, you get mean square error 3, mean square error up to n. and then you take the average of those mean square errors. Then you get your cross-validation error. Okay, so this is leave one out, cross-validation. Yeah, this is, so with this leave one out cross-validation, it fits the model with n-1 observations, which is almost the full data set, right? Comparing to the validation data set, the validation data set, which usually fit the model on half, like if you have a 50-50 split. This leave one out also produce the same result every time. And there's no randomness when you check them all. Like you check them one by one and you take the average of the mean square errors. It won't change every time you do the whole process. I mean, for the final cross-validation error. Well, the validation set method will vary dependent on the random split between the data sets. Well, why do not use this leave one out all the time? Because it's very computationally expensive, especially if you have a really large data set, or your model is very slow to fit. It's almost impossible to use leave one out cross-validation. So it's basically a trade-off, like for this leave one out cross-validation, and also that like validation set method, which is basically split your training and your validation data set. So this is a comparison between these two, and yeah, we have this particular slide for our least square regression. So for least square regression, we actually have a shortcut for leave one out cross validation. Also for this is for least square linear or polynomial regression. You can compute the leave one out cross validation error by just fitting the model once and computing this value. And this HI, if you still remember, that's our leverage for each data point. And YI hat is the fitted value from your least square fit. Okay. This is actually the regular mean square error, but with each residual divided by 1 minus HI, 1 minus your leverage. So this is the extra part comparing to a regular mean square error. Well, this is the shortcut we can have for regressions, least square regressions, for leave one out cross validation. Well, beside the leave one out cross validation, we also have this k-fold cross validation, which is a more general alternative to this leave one out cross validation. So this is essentially the same procedure as leave one out, but you divide the set into k folds or k groups and leave out one fold, one group every time. The cross-validation error is computed like same way, except that now you have k groups. Previously, we have n observations, right? Each time we just leave one observation out. So basically we have sort of n groups in that leave one out cross-validation. But here you divided your data into k groups. And every time you train your model with the other k minus 1 group and use that one group left for your for testing, and you get those mean square errors, and now we take the average of those mean square errors. That's your cross validation error. for k-fold cross-validation. In practice, you often use k equal to 5 or k equal to 10. Well, I said this leave one out is equivalent to setting k equal to n. Okay, and why we use this instead of leave one out? Because of the computation time. Like fitting the model 10 times is much faster than fitting it n times, like if n is much larger, especially if you are fitting like large, complicated models. Like every time fitting your model is slow and you have to repeat it n times. So that takes time, right? So we just normally use like 10-fold cross-validation. Okay, yeah, I also have this chart or plot to show you what a k-fold cross-validation looks like. So for example, we have k equal to 5 here. This is your whole data set again, and you just pick 5. Oh well, you split this whole data set into 5 groups, 5-fold. And each time you take one out for your testing, for testing purpose. And the next time you take the second group, take second fold for testing. The third time, take the third, and you repeat this for 5 groups. Okay, and get the corresponding mean square errors and take the average of those mean square errors. You get your cross-validation error. Okay, yeah, we talked about validation methods and leave one out cross-validation and k-folds cross-validation to now. We have to talk about the concept of bias variance trade-off for the validation, for the cross-validation methods. This is another advantage of k-fold cross-validation. So this k-fold is computationally better than leave one out cross-validation. But there is another factor, and we have to consider, which is the bias variance trade-off. Well, this leave one out cross-validation gives approximately unbiased estimates of the testing error, since we are using almost all the data points for training. And these k-folds give a intermediate level of bias because each training set contains like n minus n divided by k observations, which is basically like k-1 groups for training. So from the perspective of bias reduction, this leave one out cross-validation is better because it uses more data and gives more unbiased estimates of the error. Okay, so this is part of the advantage for leave one out cross-validation. And beside the bias, we also have to think about the variance of a procedure. So I said there is a trade-off between bias and variance. Leave one out cross-validation have a lower bias, but it has a higher variance comparing to the k-fold cross-validation. And this is because we are averaging the output of n-fitted models, that they are all trained on essentially the same data. So those models have really high correlated output. And when we average k models for the k-fold cross-validation, they are somewhat less correlated with each other. Well, because there are like less common data points they use for training. And well, you also have to know the fact the mean of many highly correlated things, they have a higher variance than the mean of many less highly correlated things. Okay, because like the effective sample size for the highly correlated data would be actually less than the actual data sets, because many of them, they are correlated. The information they contain would be actually less than the actual data sets. Just to understand this bullet, why the highly correlated things have higher variance. Like when their effective sample size is smaller, like the n you are dividing, when you calculate the variance, that n would actually be lower, would be smaller because of the correlation, and your effective sample size is smaller than n. So that will result in higher variance. Yeah, so in this way, the least leave one out cross-validation would have a higher variance because of the data you use for fitting model for training, they are highly correlated. And the effective sample size is smaller, so your variance is larger. Well, this is a comparison for, well, I haven't finished it yet. So we would consider, we would have to, yeah, what this mean, like the variance, for the variance bias variance trade-off. So we would have, we have to consider this trade-off when we choose K. And actually we have mentioned empirically choosing K equal to 5 or 10 give the test error rate estimate that suffer neither from excessively high bias nor from high variance. That is saying K equal to 5 or 10 would be a good choice to maximize this trade-off. Okay. Well, I think, yeah, I think this is for the cross-validation part for the yeah, for continuous data. And yeah, I think we can go to R. Oops, yeah, we can go to R to take a look how would we do cross-validation with R. Okay,